Well, thank you. I'm very excited to be here to tell you about the work that my group has been doing at MIT for the last 20 years now. I'm going to tell you about something called quantum magic in nanocrystals. Quantum dots are where the quantum magic happens. Quantum dots are nanometer-sized crystals of semiconductors. They're tiny, tiny crystals. They're made of thousands or hundreds of atoms, so they're bigger than an atom, they're bigger than the molecule, but they're still really tiny. And they have some very unusual properties that I'll be talking to you about today. Let's start by having a picture of what a quantum dot really looks like. Now, we can't use a regular microscope to see a quantum dot because they're way too small. You can't use a light microscope. So in order to see them, to know that we've actually made them, we have to use an electron microscope. And this is one of my students working on the electron microscope at MIT. And this is what comes out of the electron microscope. It's a little picture where each one of these little particles, these little crystals, is just a few nanometers in size. Let's start with something really huge to get an idea of scale. Something really huge, like the sun. The sun is 1 billion meters in size. Now, humans invented the meter because it's on the human scale, right? We like to measure things that are on the scale of a human. And I brought a meter with me. Come on up. There's a meter right here. Mia here is 1.25 meters tall. It's a great frame of reference. Now, compared to the sun, she's a lot smaller, right? So the sun is huge. In fact, the sun is 1 billion times bigger than Mia here. If I were a quantum dot, I would be tiny compared to Mia. In fact, a nanometer is 1 billion times smaller than a meter. So the quantum dot would be 1 billion times smaller than Mia here. The quantum dot, Mia would be like the sun to a quantum dot, to give you an idea of scale. Okay? Thanks, Mia. Okay, so now we have an idea of scale. They're really tiny. They're bigger than atoms and molecules. They're still so small you can't see them in a microscope. They're as small as the sun is big to us. How do we make them? What you see here is our pot. This is where we do our cooking. The temperature is about 500 degrees Fahrenheit, 300 degrees Celsius. Okay, so you're going to see the movie of this being made now. So there's the chemicals in the syringe here that are going to make the quantum dots. This is at 570 degrees Fahrenheit. And you see the color of the quantum dots is red now. And as it's cooking, the color is changing. It's going to get darker and darker. They're getting redder and redder as the particles get bigger and bigger. And when they're diluted in a solvent here, you can see that they're different colors. And it's even more impressive than looking at them with visible light is to look at them under UV light. So we shine ultraviolet light on them. The big particles on your right here, the red ones, are bigger than the ones on the green ones that we're taking out of the pot a little later. Okay, so there's a size difference here. It's the same material. It's the same semiconductor. The only thing that's been different is the size of the particle. 1 nanometer for the green ones, 4 nanometers for the ones that emit red. Why is that? Why is that? Well, you know other places around you where size makes a difference. For instance, when you're talking about acoustic waves. If I take a flute and I take a piccolo, they sound different. The flute sounds deeper than the piccolo. Why is that? It's because the sound wave that fits in a flute is longer than the sound wave that fits in the piccolo. The shorter the sound wave, the higher pitch you have. We also know that from organ pipes. You have the big organ pipes that can fit a big sound wave in them. They're deeper sound, lower pitch than the narrow, teeny organ pipes that are shriller. We also know that with strings. If I take a stringed instrument like this ukulele here, and I make the string shorter, the sound is a little higher pitched. Okay, where does that have to do with quantum dots? All this is the human scale. Well, it has to do with the electrons that are in quantum dots. When you think of electrons, you usually think of particles that are going through wires, powering your power tools, your chip, or whatever, little particles of charge. But if you take that little particle of charge, that electron, and you try to stuff it in a little box that's a nanobox in the size of a nanometer, it changes its properties. It becomes like a wave. It fills up that box like a wave fills up a flute or an organ pipe. This is quantum magic. This is this funny world where things don't behave the way that you expect them to behave. All right, so now I've got my boxes and I've got some electrons in there, but just like the strings on the ukulele don't sing by themselves, I have to do something to the flute to get it to emit a sound. I have to strike the particle somehow to get those electrons to behave like waves and for the energy to come out as light. Okay? So for the ukulele, I pluck it. That's how I create the sound. For the electrons, to get them to be waves, I strike them with light. I can strike them with a blue photon, or blue light, or UV light, and that creates those electrons. They become waves, and they start to emit the light. So now you know why they work. You know about the magic of quantum mechanics that makes them have different colors. And they're really little pieces of rock, so they're kind of stable. So it took us about 15 years to go through some really fundamental research to get to where we are in terms of understanding all this stuff. And about 10 years ago, we realized that if you have something that's bright, that's tiny, and that's colorful, they could also be useful. And I'm going to tell you about two uses of the particles, one in biology and one in electronics or lighting.